Professor Ramdorai Sujatha. She's the holder of a Canada Research Chair at UBC, and she works in Iwasawa theory, which may be considered a part of algebraic number theory. Before coming to UBC, she was a faculty member at the Tata Institute of Fundamental Research in Mumbai, where she was also a PhD student. She got her PhD in 1992 under the direction of Professor Parimala, who will also be speaking in the conference. I don't think she's here yet. Mathematically, Sujatha is probably best known for her work with quotes on non-abelian Iwasawa theory. And in addition to this, she has many works on the Iwasawa theory of elliptic curves and has collaborated with a large number of leading mathematicians. Amongst her many awards are the Bhatnagar Award for Science in 2004, given by the Government of India, the ICTP Ramanujan Prize in 2006, the Krieger-Nelson Prize of the Canadian Math Society in 2020, and most recently the Padma Shri, which is also an award from the Government of India in 2023. Sujatha.
Thank you, Kumar. Thank you for those kind words. And thanks to the Fields Institute team for this invitation. It's wonderful to be here. And somehow this conference crystallizes the collaborative nature of mathematics, just seeing the diversity of people, both in terms of mathematical languages and also the countries that they represent. So I'm very glad to be here. Thank you. So I'm going to be talking about Iwasawa theory in a family of ZP extensions. And I'll explain. I'll be writing partly on the board, so people who cannot read, well, don't worry. So the situation is always the following. F will be a number field. E over F is an elliptic curve. P is an odd prime, which I'll assume to be greater than or equal to 5. 3 is also okay, but I'll have to make additional assumptions for 3. And 2 is a completely different story, so which I'll keep away from. So the Burt-Swinnerton and Dyer conjecture, we all know the weak form. First, we have the Mordell-Weil theorem, which says that the rational points of the elliptic curve over a number field is a finitely generated abelian group. So therefore, one can speak of its rank, given the structure theorem for finitely generated abelian groups. We have the rank of the elliptic curves, which I'm going to denote by R of E. And then there is the Hasse-Weil function of E, and which is really an analog of the classical Riemann zeta function in the context of the motive coming from the elliptic curve. And the order of vanishing of this Hasse-Weil function at S equals 1, this is usually called the arithmetic rank. And the weak form of the Burt-Swinnerton and Dyer conjecture predicts that this algebraic rank is equal to the arithmetic rank. So to E, you can think of E, elliptic curve over a number field, and then you have two parts. So E over F, and then you have the algebraic rank of the rational points over the number field, and then you have the Hasse-Weil rank, which gives the arithmetic rank, which is the order of vanishing. This is really one of the first cases of an automorphic L function, order of vanishing at S equals 1 of the Hasse-Weil function. And then Burt-Swinnerton and Dyer conjecture is this prediction that these two are equal. Now, why should these two, which are totally different animals, so to speak, one is algebraic and the other one is built up using points over finite fields, and you can think of it as coming from analysis or coming from arithmetic, why should these two be equal? And Iwasawa theory, okay, this is what I would call the weak BSD. This is the weak form of BSD. There's a stronger form which predicts or which gives an exact formula. That's the strong BSD, and it gives an exact formula for the leading term of this L function. So this is a power series. S is a complex variable here, so it has a power series expansion. So the leading term of that power series, there is an exact formula for this leading term in terms of certain deep and mysterious arithmetic invariants attached to the elliptic curves. For instance, to give you some of the terms that will occur in that exact formula, there will be the points, the torsion points, there will be the regulator, which is really cohomological in nature, there will be the period, which you heard in the previous lecture, and then there will also be various what are called Tamagawa factors, and then of course the Tate-Shafarevich group, which is conjectured to be finite. So that weak exact formula, which is a strong BSD, it has an exact formula for the leading term of the L function in terms of certain animals associated to the elliptic curve, which themselves are conjectured to be finite. For instance, the Tate-Shafarevich group being finite is a conjecture. It's known in some cases, but in full generality, we still don't know that. Now, why should something like this be true, or why should one expect like this? So Iwasawa theory, this is, I say, p-adic in nature because you do it prime by prime. It's really, you work with a prime number. That's why I need a p which is greater than or equal to 5. So let's look at this form, the strong form, which gives an exact formula. So in that exact formula, you want to prove that exact formula. And there what you do is you say, okay, if I want to prove two things are equal, two numbers or two fractions are equal, let me look at them prime by prime. And then we'll prove that for every prime, the two sides are equal. And in doing that, as far as I know, the only systematic way to do that is to use Iwasawa theory. So that's why I say it's a p-adic theory. And it also provides a philosophical framework that explains this mysterious connection, which is predicted by the Bird-Swinnerton-Dyer conjecture. So you have this algebraic rank and arithmetic rank, and then this mysterious connection, Iwasawa theory explains why there should be such a relation. And very briefly, in plain English, what happens is you have these two that you want to relate, and then it says, so we are over a number field. And this is where it stops being intuitive somehow. You want to prove things over a number field, which is a finite extension of Q. But then the only way you can do anything at this level is by going to a big extension, to an infinite Galois extension, F infinity. And there's an object here, which I'll call X. This is really an object. And it's really a module over a certain algebra. I'll define all that. And then this has two faces. So there's one which is called the p-adic L function. So this is a function in a p-adic variable. So now this is a p-adic variable. So you can think of it as being varying over Zp, for instance. And then to this X, there's also an algebraic. Again, you can think of this as arithmetic or analytic, just as a complex L function. And here you have an algebraic invariant, which is called the characteristic power series. I'll explain all this, how they come about, characteristic power series. And then there is a conjecture, the main conjecture, which has been proved in many cases, which says that these two are equal. So you have the p-adic L function and a characteristic power series. Both of these lie in an algebra, and there they are predicted to be equal. And you know this happens in many cases. And all this is happening in this big tower. But then this is a Galois extension, G, this is the Galois group. You descend. And then when you descend, you see that the descent manifestation of this is the complex L function in the following sense. This p-adic L function, I mentioned this is over a p-adic variable. This is really a complex variable, but you have Z which is dense in Zp, and Z is also inside the complex numbers. And the p-adic L function interpolates the complex values, the complex L values for integers. So therefore you see its descent manifestation as the p-adic L function. And here the characteristic power series, somehow this is related to the algebraic rank. So these two are related because they are two faces of some object lying up there. And when you decide, you see them as the complex L function and the rank. So that's roughly what the Iwasawa theoretic framework tells us. Okay, so now what are the elements? So this X is what is called the Selmer group over this big extension. And so let me move on to the next slide. All right, so all this is going to happen in this context of infinite extension. So we need to define what's an Iwasawa algebra and so on. So from now on, whatever infinite extensions I will be working with, the Galois group will always be assumed to be a pro-P p-adic analytic group. Okay, so here. So I'll always assume that this is a Galois extension and the Galois group is pro-P, contains no elements of order P. That's important. And that it is a p-adic analytic group. So now what are the natural ways in which you can find some groups like this? So you take the cyclotomic ZP extension, which is a subfield of attaching all the p to the power n roots of unity as n varies. So you take the union of all these cyclotomic extensions of F, and the Galois group of this is Zp star, the units in the p-adic ring of integers, and then you take the cyclotomic Zp extension. So the Galois group there of F cyclotomic over F is Zp. Then another important example is this. This is roughly what I'll be talking about for a large part of my lecture today. You take an imaginary quadratic field and then take the composite of all linearly independent Zp extensions of K. So take a quadratic imaginary field. So you have Q, you have K, and then Leopold conjecture tells us how many linearly independent Zp extensions K should have. It is R2 plus 1, where R2 is the number of complex embeddings. And now because this is totally imaginary quadratic extension, it has two linearly independent Zp extension. One of them is the cyclotomic Zp extension, and the other one is what is called the anti-cyclotomic Zp extension. Okay, so then K infinity is the composite of both of these, and this Galois group G here is isomorphic to two copies of Zp2 of Zp. So it is Zp2. So now inside this, of course, because these are linearly disjoint, in principle there are lots of other Zp extensions. Okay, here's another example of another such extension. I can take my base field and I can assume that it contains the p torsion points of the elliptic curve, and assume that it has no complex multiplication. The elliptic curve has no complex multiplication, which just means that the endomorphism ring is not larger than the ring of integers. So it's just Z. And then I take the p division points of the elliptic curve. E is an abelian variety, so I can look at the p to the power n torsion points as n varies, attach the coordinates to my ground field, then I get a larger and larger extension, and then F infinity, F of EP infinity. And in this case, the Galois group is highly non-abelian. When it has complex multiplication, it's two copies of Zp, which is abelian. But in this case, it is a subgroup of GL2 2x2 matrices over Zp, and Serre tells us that it's equal to GL2 Zp for almost all p, so it's highly non-trivial, highly non-abelian. And now all these objects, LP and the characteristic power series, are really going to lie in the Iwasawa algebra. And what is the Iwasawa algebra? So lambda G for any extension like this. So G pro P, these are standard, I won't keep repeating it. Pro P p-adic analytic group. No elements of order P. And so let's again have this diagram. So I have these intermediary layers. So this whole Galois group is G, and then the Iwasawa algebra lambda G is defined to be the inverse limit of Zp, these quotients G mod Gn, where Gn varies over open normal subgroups of G. So these are the finite layers. So this is Gn and this is G mod Gn. So this is an honest group ring, and then you're just taking the inverse limit over those. So this is really a completed group ring. And when I first learned Iwasawa theory, my PhD was not in Iwasawa theory. I learned it later when John Coates came to Tata Institute to give a series of lectures. And the first question I asked during those lectures was, again, because it was so unintuitive, you're asking questions about a finite extension, why do you have to go to this infinite extension and work with these completed group rings? And he didn't know the answer. He said, oh, you know, that's what Iwasawa did to study the class groups, how they varied along a tower. And that fits beautifully to what we want to do with the motives associated to elliptic curves. And that's why we did it. And then I was coming from a background in algebra. And so I really wanted to understand why something like this could not be done over the finite extensions? Why do you have to go to the completion rather than just work over ZP G mod Gn? And the reason is simple. There's no module theory for these groupings. There's no way you can there's no way to classify modules over group rings, finite group rings. And whereas you will see now when I describe these rings, even if this is abelian, there might be something you can hope to do, but again, nothing as beautiful as what can happen when you go to this completions. And in this case, for instance, when G is ZP, then this lambda G just turns out to be the power series ring in one variable. So which from the commutative algebra point of view, it's a beautiful ring. It's a complete regular local ring. It has a dimension theory. And in general, when it is ZP to the D, then lambda G is isomorphic to the power series ring in D variables. And so this is what I'll be using. So all these objects, this periodic L function, this characteristic power series, all of these will actually be elements of the corresponding Iwasawa algebras. Okay. And I'll be working again because I want to define the Selma group. Most of you have probably seen the Selma group at finite levels because we know that the only way to get our hands on the rank of an elliptic curve is via studying the Selma group. And the Selma group is going to be defined in terms of cohomology. I'm going to define it in terms of cohomology. So let me fix, as in the previous lecture, I'll fix a finite set of primes. Yeah, I don't know why I didn't write it here. So this is again going to be fixed throughout my lecture. I'm going to fix a finite set of primes S of the base field, finite set of primes of F containing the primes above P, all the primes V above P, and primes of bad reduction for the elliptic curve. So this is a finite set, and then we'll use the standard notation, which is the maximal unramified outside S extension. Okay, so here's the picture. So we have Fs and all the extensions that I described, namely the ones coming from attaching the p division points or the cyclotomic extension, or in this case, when k is totally imaginary, the composite of all the Zp extensions, they all lie inside this. So I will usually consider my infinite fields to be inside this set, this maximal unramified outside S extension. No, honest. I'm not considering the maximal P quotient. They're just there. Okay. All right. Now, what is the Selma group? The Selma group, let me first define it at a finite level. So this is a finite extension. So the Selma group also put it here so that you can see it. So the Selma group is something defined as a subgroup. I'll put a P infinity. This is again because it's a periodic theory over L. L is a finite extension. This is inside this Galois cohomology group, Galois group of Fs. I'll just write Fs over L, by which I mean the Galois group. EP infinity, all the P division points. Okay, and Then the direct sum over this finite set now, which I'll write JV of E over L. And what is JV? JV of E over L. My V is in S. Sorry, this is in S. So this is a prime which is occurring at the base level. And I take the completions over all the primes LW, E, and this is the complete P primary part. So any prime here, when I take a finite extension, there are going to be a finite set of primes above it. And then the Galois group, these Galois group acts on those. And I complete L with respect to each of those primes, take the Galois cohomology, and then take the P torsion part, the P primary torsion part of that. And I take the direct sum over all the primes lying for each V. We do this. So the Selmer group is this. And then, of course, there's the Tate-Shafrevich group. Which is really the same thing, except I don't have an E here. I have everything outside. So let me just write H1 and just write L. This is the kernel. H1 L EP infinity. Oh, sorry, H1 L E. The P infinity now comes out, the P primary torsion, going to trivial at all the primes. So in other words, all the torsors for E over the ground field L, this field L, which acquire a point when I complete it at every completion. So this is the Tate-Shafrevich group. It's conjectured to be finite. We know it in certain examples, but we don't know in full generality that that's a finite object. Now, why are these two relevant? Because the only way you can get to understand the rank of an elliptic curve is by this exact sequence. So I'll go to the next. So you see this exact sequence here. You want to understand the Selmer group. That's the only way you can get at this model way group. The model way group is here. This is the torsion. This is the points of the elliptic curve, the rational points. But the only way you can get at them is for every prime, you look at this exact sequence. 0, E of L, tensor QP mod ZP. Then this lies inside Selmer, E over L. And then this part here is the Tate-Shafrevich group. So it's very strange. You don't understand this. You would like to understand this. And the only way you can get at this is by analyzing this. And then you try to figure out what are the objects here which lie here, which means what are the objects here which go to 0 here, and so on. So that's descent. That's how you play it at a finite level. But like I said, this is an exact sequence of all these are modules with an action of this Galois group. So this is really an exact sequence of Galois modules. And I can take the direct limit and then define the same analogs over an infinite extension, which is what I have said here. So if I take an infinite extension L over F with Galois group G, then I can take the direct limit over these exact sequences at the finite stages. Then I can define the Selmer group at this infinite level exactly in the same way. That's a subgroup of this H1 Galois cohomology group. And then this makes sense as well. You take the direct limit here. And then this is the kernel of this natural map. These are the restriction maps. Here you have this global Galois group. Here you have the local Galois groups, the decomposition groups. So there's a natural map from here to here given by the restriction. And this is the kernel. Now, as we go to a finite, from the finite extension to the infinite extension, at the finite layers, these were all exact sequences with an action of these Galois groups, these finite Galois groups. And when we move to the infinite extension, they naturally acquire a structure as modules over the corresponding Iwasawa algebra. Now you have an infinite extension. And I've defined the Iwasawa algebra for that infinite extension. And now these modules, these become modules over the infinite extension. Each of these. So therefore, if I can understand this as a module over an Iwasawa algebra, and then I can understand this submodule, then I would have some idea of the model way group, but over this big extension, over an infinite extension. But then I perform descent to come and understand it over the finite layer. So it seems like a convoluted process, but like I said, that's the only way you can get to these model way groups at the finite layers, because you cannot work with modules over group rings. But now, why can you work with modules over these completed power series rings? That's because there's a very beautiful theorem. There's almost a structure theorem. It's a weak form of a structure theorem, which was originally done by Iwasawa in a rather ad hoc fashion. But then Sayre immediately spotted the algebra behind it, and Sayre gave a precise statement for the structure theorem of finitely generated modules over Iwasawa algebra. So let me first deal with this case. So we have G is ZP. So typically this occurs, for instance, when I take the cyclotomic ZP extension. Then I mentioned that the algebra, the Iwasawa algebra is thus the power series ring. And then you have a finitely generated lambda module, lambda G module. I'll use this notation tilde to say that these two modules are pseudo-isomorphic, which means that there's a module homomorphism between them, such that the kernel and the co-kernel have codimension at least 2. Codimension with respect to this ring, right? Both of these are modules over Iwasawa algebra. In this particular case, this ring itself has dimension 2. So codimension 2 just means that the kernel and co-kernel are finite. So up to ignoring finite modules, the next theorem will tell us that there is a nice way to describe modules over this Iwasawa algebras. So this is the structure theorem. So let M be a finitely generated lambda G module, then G is ZP. Oops. So the Iwasawa algebra is a power series ring in one variable. Then up to ignoring finite modules, this tells us that it's almost like the structure theory for modules over ZP. You have a free part, lambda G to the power M, and then you have those where you look at the prime P, ZPT. So you have a prime, so you look at the number of time powers of P occur. And then after that, there is this, which is each of these Fj's are a distinguished polynomial. This is a distinguished polynomial, by which I mean it's a monic polynomial, all other coefficients are divisible by P. And though this is in the power series ring, so this sort of brings us to a finite layer. So you have these elements here, the polynomials raised to certain powers. So the real thing to do is to think of all these as height 1 prime ideals, because this is a regular local ring. So it's a unique factorization domain. So all these denominators here are really height 1 prime ideals in this ring. And then you go back to your usual structure theorem over ZP, principal ideal domain. There, this is sort of an extension of that, except for ignoring finite modules. And therefore, this allows us to define invariants. So the first is the rank. That's the free part here. And then the mu invariant is you count the number of times P occurs with powers. So you sum all the powers of P. That's the mu invariant. And then there's the lambda invariant, which is got by multiplying Mj with the degree of these polynomials and then summing them up. So this is somehow the free part up to Zp. This gives you, counts the number of Zp copies, and this counts the number of Fp double bracket T copies. Okay, so these are important invariants, and what they do is they really encode information about the model way ranks as you climb up the tower. So you have this tower, and the Iwasawa algebra is defined with respect to this Galois group. And if I understand these invariants, they provide information on the ranks of the model way groups as I climb up this tower. Model way rank, you can get the model way ranks, well, roughly, not exact model way, but the way to do it is, again, you're right, you perform descent, you come down to the Selmer, but then some cases you can predict the growth. You have a bound on the Selmer, therefore you push it to a bound on the model way. Okay, Now this is again a discrete, all these are discrete modules. When I take this infinite extension, all these modules, the Iwasawa algebra itself is a compact topological ZP algebra. And this sequence is an exact sequence of discrete modules here. This one here, all these modules are discrete. But it's nice to work with compact modules, so we usually take the Pontryagin duals of this, and I'll denote the Pontryagin duals by xp infinity, and that was the x that I originally wrote. This module at the top, which has two faces, an algebraic and an arithmetic face, which gives us the p-adic L function and the characteristic power series, and when I descend them, then they are related to the complex L function and the model and the Selmer group, and from the Selmer group you come down to the model way group. So that's roughly the larger picture. Now therefore I'll take Pontryagin duals and I'll denote that Pontryagin dual by xp infinity of E over L. And now therefore I can ask, what are these invariants for this? Given an elliptic curve, then I've now cooked up a module, namely the dual Selmer group. I have the dual Selmer group, and then the structure theorem that I mentioned, it's not at all difficult to see that this is a finitely generated module over the Iwasawa algebra, this dual Selmer group. And it's in fact compact. So therefore you have invariants. You have the rank, you have the mu invariant and the lambda invariant. And the context that I am going to be working with for the rest of the lecture is this following question, which really relates to this family of ZP extensions. So I'm going to come back. So my K over Q is an imaginary quadratic extension. And then I take, because my Leopold's conjecture, I take the composite of all the ZP extensions. So I have this natural extension, which is G, and this is isomorphic to two copies of ZP. And in between here and here, I'll have a multitude of ZP extensions, which I'll denote by H infinity, H prime infinity, and so on. So this part, so let me zoom in on one of those. So I'll have H infinity. This Galois group is H. And so this is the fixed field under H. H is isomorphic to ZP. And then this quotient here is again, okay, this is a quadratic imaginary. So this is again a ZP. I'll call this gamma H. So this is ZP. Now I'm interested in the following question. I have an elliptic curve. For each of these intermediary extensions, I can look at the dual Selmer group. And I have the invariants, the mu invariant and the lambda invariant for each of those in that family of ZP extensions. What can I say about them in that family? So to do that, we use this very nice observation of Greenberg, who did this a long time ago. And okay, I should mention that all the results below, which is framed in this context of working with imaginary quadratic extensions and the composite of all ZP extensions, they're all joined with Zoran Kleiner and Ahmed Ali Matar. So this is, as I mentioned, this is the context in which we are interested. So for each of those, I have the associated invariants, the mu invariant and the lambda invariant. And now note that this subalgebra, this Iwasawa subalgebra, is viewed as a subalgebra of this larger Iwasawa algebra. You have the Iwasawa algebra for the whole Galois group G, which is ZP2. So that's a power series ring in two variables. And then when I look at H, that's a ZP, and that gives me a subalgebra, which is a power series ring in one variable. And Greenberg made this observation a long time ago. He said, look at the set of all the ZP extensions contained in K infinity. So this K infinity is a ZP2. I look at all the intermediary ZP extensions, and they are in bijection with the projective space over ZP, with P1 over ZP. And what is the map given by? Now G is ZP2, so it's topologically generated by two elements, topologically free on two elements, sigma and tau. And if I take an element P1 ZP, AB, then the corresponding H that I get is the closure of sigma to the power A, tau to the power B closed inside G. So this gives a codimension 1 free subgroup of ZP2, and so therefore gives me an intermediary layer. Not just that, this is not just a set bijection, but you can actually give a topology on E so that this even becomes a homeomorphism in a suitable sense. So this was an observation made by Greenberg a long time ago, and this is the topology. So you take an intermediary layer. What are all the other ZP extensions that are in a neighborhood? They are those which look like your extension up to n. So that's what this really means here. So a base consists of all extensions such that the extension degree over the base field k up to p to the power n. This extension degree is at least p to the power n. So in plain English, it consists of all ZP extensions contained in K infinity that coincide with L up to the nth layer. Now here is a conjecture that Coates and I made a long time ago. So you have this dual Selma group over this big extension. Now we know in many cases that it is a torsion module over the corresponding Iwasawa algebra. We always know that it's compact, finitely generated. That's not a problem at all. That's just Nakayama's lemma. Fancy version of Nakayama's lemma will tell us that it's finitely generated over lambda g. But there is a stronger conjecture which says that once I kill the P part, remember there was even a structure theorem for this. You had a P torsion part where the denominator was P, which was giving us the mu invariant, and then the ZP part. So this MH of G conjecture says that if I kill the P primary torsion part, then what remains in fact has to be finitely generated over this subalgebra. Okay. And one way this can occur, for instance, it's again easy to see, not difficult to see, that if I know that the Selma group, when I take this intermediary layer and the mu invariant here is 0, if the Selma group of the mu invariant here is 0, then that automatically forces MH of G conjecture to be true. Now, what is interesting in our work is that there is another conjecture of Mazur. Okay, before that, let me make these observations. So again, now there is this family of ZP extensions. So there are natural questions which we can ask. Where are they? Suppose I know something about one family, what can I say in a neighborhood? Now there is this, what we can say is for this subfamily, I take this subset here, H, and I make these assumptions. These are all the intermediary ZP extensions where I need to make these assumptions. No prime of S splits completely in this extension, in this intermediary fixed field. Every prime of K above P ramifies in this extension. And then the Selma group at this layer is torsion as a lambda gamma H module. It's torsion over this remaining part. So I'm working over an intermediary ZP extension, and I take all the ZP extensions which satisfy these properties. Now, first question is does such a family exist? Is it non-empty? And the proposition we show is that it's non-empty. And in fact, it's non-empty for almost all but finitely many points in the P1. Remember, I identified P1 with this family of ZP extensions. So this is not asking for too much. It holds almost always. Now, there's this old conjecture of Mazur, which says that the model Weil rank of the elliptic curve stays bounded along any ZP extension of the imaginary quadratic field unless that extension is an anticyclotomic extension. And then plus the root number is -1. So what is the root number? We heard about the automorphic L function, that is a Hasse-Weil L function. It satisfies a functional equation, and the sign in the functional equation is the root number. So unless the root number is -1 and the ZP extension is anticyclotomic, that's the only case in which the model Weil rank as you climb up this tower does not stay bounded. That's a conjecture of Mazur, and our main result is this. So we assume that this family is non-empty, and I said that this is not a strong assumption. It is non-empty in a large number of cases. In fact, it's non-empty for all but finitely many points in P1 ZP. And then the following statements are equivalent. The MH of G conjecture is true. That's the first statement. Now this, you can ignore this B because I didn't define the mu invariant over the larger extension. But this tells us that this happens only if the lambda invariant this is bounded in a neighborhood of this extension. So we are looking, remember, we are looking at a family of intermediary ZP extension. And then the model way rank is related to the lambda invariant. And it says that if the lambda invariant is bounded as it varies in a neighborhood of an element, then the MH of G conjecture is true. And then this last part also tells us how big the Selmer group can be. If in addition, if we know that there are only finitely many p torsion points even over this ZP extension, then it means that the dual Selmer group and therefore the model way part actually sits inside powers of this subalgebra lambda h here raised to this power, the lambda invariant, which comes from the structure theorem. And this lambda h is at least the lambda invariant over the intermediary layer. And one of the consequences of this theorem is that it tells us the number of ZP extensions where the rank of the elliptic curve, where the rank of the model way group as you climb up the tower does not stay bounded. And this is again phrased in terms of the MH of G conjecture. So in other words, suppose the MH of G conjecture holds for an element in this family ZP extensions, then we can bound the number of ZP extensions where the rank is unbounded. So in this family, knowing information about one ZP extension, you try to get information about other intermediary ZP extensions. Now, and here are some concrete cases where this has connections to Mazur's conjecture. So assume that P is odd. When the rank is 0 and Tate-Shafrevich group is finite, then Mazur's conjecture is true. So this gives us cases when rank 0 and Mazur's conjecture being true. In the rank 1 cases, we use results of Kundu, Debanjana Kundu and Anvesh Ray, where again we can say when Mazur's conjecture holds. So you need slightly more hypothesis here. P odd, unramified, and then the rank is 1. Again, you need to assume that the Tate-Shafrevich group is 0. And then you have the p-adic regulator, which shows up in this exact formula that I mentioned. This is a cohomological invariant. It's also a k-theoretic invariant and so on. And you take the p-adic valuation of not just the elliptic curve, but you also take the quadratic twist of the elliptic curve. And you assume that the p-adic valuation are at most 1. And then make these other technical hypotheses, primes dividing the conductor split in this quadratic extension. And this p does not divide the Tamagawa numbers of both E and the quadratic twist. And then it does not divide the number of points over the reduced elliptic curve. Then Mazur's conjecture is true. So you get conditions where Mazur's conjecture is true, both in the rank 0 case and the rank 1 case. And one thing I learned from Coates is that any theorem that you prove is not worth proving unless you can give examples where the hypothesis holds. And this is the hardest part. Okay, the theoretical part is also not easy. But then finding examples where all the hypotheses really hold, and I'm never an expert and my collaborators thankfully always know how to handle SAGE and so on. So we could come up with a large class of examples. So I'm just giving you a sample of some of the examples where Mazur's conjecture was not known. Take the elliptic of 43A1, this is Cremona's nomenclature. Take the quadratic extension Q square root of -3, these are the primes, and these are the other examples. For all of these, you can show that Mazur's conjecture is true. And this was not known before. And I'll close here by saying all this was in the ordinary setting. One of the assumptions I had was that the elliptic curve has good ordinary reduction at the primes above P. We have corresponding results when the elliptic curve also has super singular reduction. That's more technical, but I'll stop here. But we have similar results there. Thank you.